Hi, everyone. Am I on?
You're good.
Good. So, this is my very first time in this part of the country. I've never been to Washington before, and I don't know any of you. So, thanks for having me. Super excited. I'm doing a little roadshow this week, and this is my first stop. I'm really excited to be talking about this open source project that I've been developing for a couple of years with a lot of help from users and other contributors, which is Parquet. So quick agenda for us, just so that I know my audience. Who has ever heard of Bloom filters before? Nice. Now, who has ever used a Bloom filter before? Cameraman over there. And who has ever implemented a Bloom filter? Hell yeah. All right. Well, for all of you who've ever been through the pains, I hope that you still have something to learn today. For everyone else, I'll take you through my journey learning about Bloom filters. So, what they are, what kind of performance bottleneck we often run into when we're working with Bloom filters, and optimizations that I've implemented in Parquet, and then we'll see some benchmark results on the effect. Quick slide about me. I came from France in 2011, moved to San Francisco, started working as a software engineer. I started working with Go specifically over 10 years ago, and I've been developing with the tool, also contributed to the project. I implemented the WASI Preview 1 port, I think 2 years ago, and also a bunch of open source, authored a couple of projects. Parquet is like the main one that I maintain now, and kind of like shifted between startups and big companies through my career. And last year I started a company myself called Firetiger, or co-started, I should say. And Firetiger is a specialized data lake focused on telemetry data. So we're ingesting open telemetry signals into Apache Iceberg and enabling per customer monitoring for SaaS businesses. So if any of you are working at SaaS businesses and then you'd like to do more with your telemetry data, maybe we can talk about this after the presentation. Apache Iceberg, other show of hands. Who has ever heard of it? Yeah, over there, fewer than Bloom filters, which is encouraging. When Apache Iceberg's newer, it can do a lot more things though. So it's an open table specifications. Basically, you can think of it as, what if you could put your SQL database on object store and then plug whatever query engine you wanted on top of it? So that's kind of like what Apache Iceberg helps you do. And it's very Java-oriented ecosystem, but we've been working on a Go implementation that we're going to open source in a couple of weeks. So I'm looking for maintainers. I've got a couple of friends at Confluent already jumping on the ship. So if you're interested in this type of tech, we should also talk. And why this is relevant is because underneath, Iceberg uses Parquet as the file format. And the Bloom filters we're going to talk about today are the Bloom filters implementation in Parquet. What challenges am I facing? So with telemetry, we typically have very high data volumes on the write path, right? You're getting tons of logs, metric data points, tracing spans, and they tend to have dimensions with very high cardinality. So think of like some of the columns have, a lot of unique values. And something that's unique about telemetry is most of the data is actually never read, right? Like when you're thinking about your central database for your application, you know why you're putting the data in it because you know you're going to need it, right? With logs, you're just sending signals, and then maybe sometimes they're going to be useful. But in my experience, 95% of the time, the data is just left on storage. So it's very critical to be able to I'm seeing you nod. You've suffered the same pains that I have probably, but it's very important to be able to ingest that data efficiently and not for the system to scale, right? The other part of the challenge is that when you actually have to query some data, you end up with this very giant data set that you need to extract information from, right? Like, it can be petabytes of data when you're just looking for a single record. So let's talk a bit about Bloom filters and how they help in this situation. So Bloom filters are a probabilistic data structure, and they answer a very simple question, which is a value part of a set or not? But the way they answer it is a little special. They don't tell you yes or no, they tell you no or maybe. And so you can choose like how certain you're going to be on that maybe, basically, based on how much data you write into the filter. And so these query examples are what filters are good at helping with. So if you're doing a point lookup for like something with a specific ID, the filter is going to help you identify where the data lives. Or if you're doing something where maybe you're matching a set of records that have a certain key value pair attached to them, that's also where Bloom filters are useful. So they accelerate queries by reducing the number of files that we have to check to look for the data we're interested in, right? So think about, your data lake is going to have thousands of files, and you're looking for a specific value. Without a filter or any ordering, you have to go and look at all those files and check if the value exists in each one of them. So the filter is basically going to allow us to only pick the files that have the highest probability of containing the value that we're looking for. They're also very memory efficient because you can think of them as a lossy compression scheme where you take any value of any size on the input and then you compress it to a set fixed number of bits. So the size of the filter can be fixed, and you can encode values of various size. So it doesn't change based on the input shape. And so this table kind of highlights how many bits you should put per value in the filter depending on your tolerance for false positives. So for the use cases that I have, usually 1% is what I'm looking for. So I'm going to be around 10 bits per value written to the filter. Very conceptually, this is how Bloom filters get implemented. So they're just a byte array, right? You're going to have some space in memory of contiguous bytes. And then there are two operations you want to do on it. One is inserting a value, and the other is going to be checking if a value is part of the filter. And so the first step is hashing that value, right? You're going to have a string maybe of arbitrary size. We're going to condense it to be a number so that you can manipulate it. And then you want to put that hash value somewhere on the filter. And I wrote this without testing it. It's roughly what it is, but you get the idea. You hash it, you put it within the filter, and then you find which bits, which byte and which bit you're supposed to set in that byte array to determine if the value is, or to tell that the value is in it. And then same thing for checking, you're just doing the reverse operation at the end. So instead of writing, you're just reading if the value is 1 or 0. Yes?
If the number of distinct values you need for the filter goes up a lot, do you just make a longer filter in the future? Because otherwise all the bits could be 1.
Yes. There's a formula for the ideal filter size based on the number of values you expect to be writing to it. And then the number of bits per value. So you can the bigger you filter, the fewer chances of false positives. The more bits per value, the fewer chances of false positives, and those are the two dimensions that you play with to optimize for size or probability. Cool. And so this shows how to set one bit in the filter, but typically you're going to have, like I was saying, in my case, 10 bits. So you're going to do this 10 times. So you'll rehash the value and with a different hash function, and then you'll be setting a different bits. And so when you're checking if all the bits matched, oh, it means that the value is very likely, unless we didn't get disconnected, very likely part of the filter. And if at least one of the bits didn't match, it means that the value wasn't in it. In the context of Parquet and Data Lake, the Bloom filters help us skip the parts of the data set that we're not interested in. And it's kind of like two steps. First, you test for the probability that the value exists in a file. And then for the remaining set of files that you've identified, you go and actually open them and then look through the data to find what you're looking for. So let's do a little bit of performance analysis on this, I won't say intuitive implementation that I showed. And there's typically three aspects of it that are going to hurt performance. The first one is the heavy use of modulo, right? Like you've got this hash value, you want to compress it to fit within the filter. And to do this, you apply a modulo operation. And then you have to do this for every bit that you're going to write to the filter. So you're running a lot of modulo. Do you have a question?
Yeah, just to make sure I understand how this is being used. So you're putting every record in a file in a Bloom filter per file, and then checking against each file's Bloom filter when you're going to look up?
Yeah, so in Parquet, the Parquet specification actually has a way to write the Bloom filter directly into the Parquet file. So there's a little bit of metadata in the Parquet footer that tells you where the Bloom filter lives. So you don't need to maintain a separate file. It can actually just be part of like a file that contains the filter for its own data. Second problem that we run into in terms of performance is hashing. Like I was saying, there's a first step is hashing the value. If you want to write 10 bits to the filter, you need to hash the value 10 times with 10 different hashing functions. So this can become very costly, especially when you're writing 1 million records per second. A lot of your time is spent hashing value and then performing modulo operations. And then the last one is more subtle, but it has to do with how CPU caches work and where the bits are being written in memory. So for modulo operation, the reason they're slow is because in CPUs, it takes like 30 to 50 cycles to run one modulo instruction. And so this is one of a special case arithmetic operation where when you're on a critical code path, you don't want to be running it too often because you're going to be spending all your CPU times stalling the CPU pipeline, just computing the modulo instead of being able to run cheap operations like add or shift. And just the order of magnitude is like 30x difference. So it's significant. Second bottleneck, like I was saying, if we're running a hash of the input, of each input value multiple times to generate multiple bits in the filter, then that increases our baseline cost, right? There's a huge overhead, which is just hashing the values over and over and over again. And the more precision we want from the filter, the more hash we have to perform. So, and then lastly, why are CPU caches important here? The mental model that I use is whenever you're writing something to memory, you have to go and read it first, right? Like the CPU is going to go and read a chunk of contiguous memory area, load it in its cache, do the mutation there, and then ship it back to memory. And if you're doing this for every bit that you're writing to the filter, you end up incurring the cost of that read and write latency to main memory every time. So if we're doing it 10 times, we're already at like 1,000 to 3,000 CPU cycles spent on doing nothing but waiting for memory to arrive and then sending it back. Yes?
Just to clarify, you're concerned about capacity misses when building the bloom filter, not on
Yes, right, yeah. Which happens also on reads, right? If you have a very large, like 100 megabyte filter, and then you're going to check bits at random locations, the CPU is not going to be able to predict where, where the next bit is going to be. So you're incurring that, serialized latency on the write path and on the read path. So how do we solve this? Well, the good thing is Parquet actually has kind of solved this already. And I thought it was important to understand the problems, just to understand how much we get out of the box by using the design of bloom filters in Parquet already. What they have is something called the split block filter. And the way it works is it chunks the filter in 32-byte blocks. And the guarantee is that whenever you're inserting a value in the filter, it will only touch one of the 32-byte blocks. So remember I was saying, if you're touching a random area of memory, you're incurring the cost of touching main memory for every bit. But now we're able to compress this into a single contiguous 32-byte chunk. That means that we've amortized the cost. No matter how many bits we have in the filter, they will always touch a single block, so we'll always pay a cache miss once per value. The second thing that is in the Parquet bloom filters is a two-step hashing. So instead of doing one hash for every bit that we're going to write, we're going to hash the value once, and from this hash value derive n different bits within the block. And the way it works is it uses the xxHash algorithm, which is pretty fast. Apply it once on the value, and then use the result of this and multiply it by 8 different salts to find the 8 bits in the 32-byte block where they should be set to 1 in the filter. Question?
Dumb question. Why 32-byte jump instead of 64? Because I thought cache was.
So I don't know why, but it's very convenient. The spec doesn't give you all the details, and the link to a paper, and that link that I put here is actually the link to the Parquet specification. So you can probably figure out all the answers later. My understanding is CPU cache lines tend to be 64 bytes. So if you're taking a 32-byte chunk and it's roughly a line, you're somewhat guaranteed to be touching a single line and therefore incurring a single latency cost when you're reading from memory. Where it's interesting as well is 32 bytes the size of a AVX2 vector registry, and this is why we made it very fast. So very first optimization that we use in Parquet had nothing to do with low-level stuff. It's all about software design, and it's about taking a data-oriented design. And I've put this link as kind of like the reference in the topic. I know probably a lot of you have watched it before. The TLDR, and the way I would summarize it, is that if you're working on arrays of data, you can amortize the cost of crossing abstraction layers versus if you're working on individual items, right? Like think of if you have a method that will return, take one value as input and return one value as output. If you want to call it n times, you pay the cost of calling that method n times. Versus if it takes an array of outputs and an array of input, now if you put 10 items there, then you've amortized 10 times the cost of calling that method. So that's like the essence of data-driven design, and then we take a huge advantage of it in Parquet Go to really maximize throughput, and we'll see how we do it with bloom filters as well. Second type of optimizations that we put in are all based on using SIMD instructions. And so this is where the AVX2 instruction set comes into play, and why the 32-byte size of bloom filter blocks is very important. It's because we can map a single block to a single CPU register, and most of the operations can be applied using vector instructions on those registers. So this is the result of a first benchmark. And so there are two things that I want to highlight. First of all, kind of like the raw performance improvements we get is in the order of 30%. So you can think of this as inserting one value into a block, a 32-byte block. The second one, which is even more interesting, is this insert bulk, because this is where we're taking advantage of data-oriented design and like working in arrays instead of working on individual values. And here we're reaching not like linear improvements, but like almost like exponential improvement compared to working on individual values. And if we look at the throughput improvements, we're at 5 gigabytes per second on a kind of like scalar implementation of the algorithm. And when we go to a vectorized implementation, we reach over 30 gigabytes per second. I run this on a Ryzen, like AMD Ryzen, like the latest ones. So the numbers are representative of the perf that we get nowadays. And for the curious, I linked the files, the source files where all this assembly code lives, but it's optional reading. Cool, so this kind of gives us the ability to like read and write those hashed values into the filter extremely fast. But the step before this is actually hashing those values. And so we're using xxHash because that's part of the Parquet spec. We don't really have a choice. But there's still something that we can do about that. xxHash is going to be very effective on large payloads. Like, so if you have strings, there are a couple of hundred bytes, maybe a couple of kilobytes, you're going to get, 15, 30 gigabytes per second throughput when you're trying to hash those values. In practice, for my use cases, I often have very small values. You can think of, like a trace ID, for example. It's 128 bits. It's fixed size also, or like a span ID, or like things that are not variable size basically. And what we do is like we once again leverage data-oriented design here to work on arrays and perform xxHash in parallel on input and output arrays. So highlight of the kind of like the function signatures that we use internally. This one is like kind of what I was talking about with, you can think of this as an array of trace IDs as input, and the output are going to be all the hashed values for those inputs. And here again, we're getting, like extreme performance improvements from kind of like the naive, like scalar, like pure Go implementation yielding a gigabyte per second. The computing xxHash in parallel on those trace IDs is performed at almost 12 gigabytes per second. So that's a significant improvement. And then when we combine all of this, because we need to perform the hashing first and then insertion into the filter, the end result is a almost 6x improvement. So you can think of it, if our fleet size to ingest all this telemetry size was 60 containers, we shrunk it back to 10, which is a major improvement. So to wrap it up, there was a lot of like key insight that were required, I think, to achieve all those performance improvements. One is really understanding the hardware, right? Like when we are trying to make the machine do more work, we kind of have to like play its game, and like knowing about how CPU and memory interact, understanding, like how to leverage CPU instructions. This is really critical, and also, as software engineers, thinking about performance per run not just as like a vertical optimization, but also something that we can just bring into the design of the software through approach like data-oriented design was very important in Parquet Go, at least. So that kind of wrapped it up. I'm available if there's more questions. Thank you so much for asking inline as well. And can I say something about Firetiger?
Yeah, go ahead.
That we're also hiring. So if any of you want to move to San Francisco, come talk to me.
Any questions?
What's the license on Parquet Go?
MIT, I think. Or Apache 2, one of those.
Both good.
Yeah. Yes.
Have you benchmarked using the AVX-512 registered in your implementation?
Yeah, there's a bunch of AVX-512. Or actually, the xxHash optimizations use AVX-512. I think I tried to do it with AVX2, but there's some instructions were missing, and it was just simpler to do it with 512. And there's a bunch of encodings and other optimization in the library that use it. Yes?
I wasn't quite following when you mentioned like these 32 byte chunks. Is the idea like, oh, you want to mutate these 10 bits, so we always mutate 10 within these 32 or something?
Yeah,
How do we achieve that?
yeah. Sorry, I maybe skipped a few steps here, but I think you got the idea. So when you insert a value in the split block filter, all the bits that you're going to write will be within a single 32 byte chunk. And so you can load this chunk, mutate it, and then write it back to memory. And this is like a single memory load. Most of the time, a single set of instructions to set all the 10 bits within this chunk, and then a single memory write to send it back.
Yeah. Is it like really grueling detail how we end up coming down to these 32, or like I would have thought that most of the like entropy capture comes from like spreading over the large array and not.
It's the math works well because the number of bits in Parquet is fixed to 8. So you have 256 bits, you're setting 8 bits, and then you're sizing the total size of the Bloom filter based on the number of values that you're going to have, right? So you're going to have more blocks if you want to put more values, but the ratio of the number of bits per block should remain somewhat constant.
Do you have to check all the split chunks on the lookup, or do you know a priori which one?
You know which one you have to check. So there's an extra hashing step. So sorry. So you're hashing the value, and then using that hash value to figure out which block it's going to belong to. And there's a little bit of like bit shifting that happens to do it quickly. And then you're computing all the bits within that block. So yeah.
You mentioned that like you can scale the Bloom filter for the probability that you care about, but if you have fixed size blocks, would that mean that you only have a fixed amount of entropy? Because you said you have a set number of bits and then a set number of blocks. And
Yeah.
like, oh, if you have 8, it would be like, oh, your first block is like 1 block out of however many you have, but then the second bit is like 1 out of 2 to the 32 instead of 1 out of 2 to the size of your entire Bloom filter, right? Like, once you have more collisions, because like you only select 1 block and then multiple bits only inside that block instead of multiple bits in the entire Bloom filter.
So the distribution of values to blocks is roughly even, right? Because you're going to hash the value, that gives you a well-distributed hash.
Sure, okay.
And then you use that hash to find the block in which you're going to write the bits. And so,
Right. Doubling the number of blocks is the same as doubling the size of the block.
yes.
Any more questions?
Cool. Let's get another round of applause.